All right, so let's do our review of Chapter 7. So Chapter 7 is dealing with all the things related to the periodic table, right? Chapter 6 was all about atomic theory. Chapter 7 now is the periodic table. So as we use our electron configurations to place our elements on the periodic table, we get some consistency in properties and relationships and things like that, and that's what the periodic trends is all about, and that's what makes our periodic table useful to us. So the main concepts of Chapter 7 is learning what causes atoms to be larger and smaller and how that affects how the atoms behave when they interact with other atoms, right? That's really what the periodic trends is all about. So the first part of this is what causes our atoms to be bigger and smaller. So we know that energy levels is a huge part of this, right? The more energy levels an atom has, the bigger it's going to be, because those inner electrons are pushing the outer electrons away farther and farther. And so the reason why those energy levels require more energy is because the electrons are farther from the nucleus. And the farther from the nucleus they are, the more energy they have to be able to stay there. All right, so energy levels is the first part of this, right? More energy levels equals bigger atom. All right, the second part of this that we have to talk about in our discussion is the effective nuclear charge. Right, the effective nuclear charge is the effective attraction from the nucleus that the electrons are feeling. Right, there's a balance between the repulsion from electrons and the attraction to the nucleus for those outermost electrons. So the effective nuclear charge is a way to calculate what that actual value is of the attraction that the valence electrons feel for the nucleus. So the best way to think about it is that the inner electrons surround the nucleus and repel equal to the amount that the protons are attracting. So if you have 10 electrons right around the nucleus, that means the first 10 protons attraction is kind of nullified. And so only the additional protons past that actually matter, right? So the higher the effective nuclear charge is, the more the electrons are going to get pulled inward and the smaller the atom's going to be. So higher equals smaller atoms. So why does this matter so much? Well, the size of the atom is telling us about how strongly those outermost electrons are going to be attracted. So the bigger the atom is, the less those outer electrons are going to be attracted. The smaller the atom is, the more the electrons are going to be attracted, right? So what's the need for us to know that? Well, remember that the big overarching idea here is larger atoms are more metallic. Right? And smaller atoms are more non-metallic. Okay, why is that? Okay, because larger atoms are going to tend to do a bunch of things. First of all, larger atoms will not have as much of an attraction for the outer electrons. So what does that mean? Well, that means that they're going to have low ionization energies. So remember, the definition of the ionization energy is how much energy it takes to remove an electron from an atom. So large atoms, those electrons are way far away from the nucleus, so it's not going to take a lot of energy for you to go reach in and pull out that electron and pull it the rest of the way away from the nucleus, because they've already had to put a lot of energy in just to get to that point. They're already pretty far from the nucleus. It's only going to be a little bit of energy after that to get it to be completely removed. So large atoms have low ionization energies. What does that mean? They're going to tend to lose electrons. If they're going to tend to lose electrons, they're not going to be very good at gaining them or attracting them, right? So they're going to have low electronegativities. So when they're involved in a covalent bond, they're going to be the ones that tend to let the electrons drift away from them, right? They're going to be the ones that are going to be more positive in a covalent bond. Or if they let the electrons drift away from them completely because the other one is so much stronger, then they're going to be the ones that are going to end up having the positive charge completely when they form an ion, right? So there's the first thing that we look at. So they tend to lose electrons, they have low ionization energies, low electronegativities. So what about smaller atoms? Well, I'm not going to write it all up here, but you should be able to get from this that smaller atoms are going to have a high attraction for their valence electrons, right? That's why they're so small, because the effective nuclear charge is really, really strong, so it's pulling the electrons in, or they have fewer energy levels, so the electrons are close to the nucleus. Therefore, they're going to have high ionization energies, which means it's going to be really hard to remove electrons from it. They're going to tend to gain electrons rather than lose them, or at least share as another possibility. And they're going to have pretty high electronegativities because they are going to attract electrons their own really well. They're also going to start to pull on other people's electrons and attract them really well too, right? So energy levels, effective nuclear charge explains whether they're metallic or non-metallic, and these are some of the properties you get out of that. So let's look at some examples. All right, simple example is, let's compare calcium to barium. Okay, what would we expect? Well, they're both in column 2, both alkaline earth metals. Okay, so when you compare it to each other, we know that they are going to be large. All right, well, whatever. So calcium and barium are in the same column, but barium is farther down the column. So what does that mean? It means barium has more energy levels. Right? Barium's in row 6, and calcium's in row 4. And so calcium is going to be much smaller than barium because barium has more energy levels. So barium is larger, which again also means more metallic. All right, what about effective nuclear charge? Well, both of them are in column 2, which means both of them have 2 more protons than inner electrons, right? We're not talking about the valence electrons, we're talking about all the ones inside of that. So calcium has 20 protons and 18 inner electrons. Barium has 56 protons and 54 inner electrons. So both have an effective nuclear charge of +2. Okay, so that's not going to have any bearing on how they behave as much as the number of energy levels does. All right, so what are we going to find from this? We're going to find that barium has lower ionization energy, more likely to lose electrons. We also know that barium will have a lower electronegativity, less likely to gain. Okay, electron affinity. The electron affinity is the energy transfer that happens when they gain electrons. I'll just write it down. Well, which one's going to have a harder time gaining electrons? They're both in the same column, so they're both going to end up going into another energy level, or sorry, another sublevel when they gain electrons. Which one's going to have a harder time doing it? Well, the one that already doesn't want its own electrons is going to have an issue with gaining more electrons. So the electron affinity will be more positive for barium, which a lot of times we say that it has a smaller electron affinity. So this is more positive, which means it's going to be more endothermic for barium to gain electrons than it will be for calcium. So it's less likely for barium to do so. And that should make sense based on the other things. If you look at the ionic radius, we would expect barium's ionic radius to also be larger. Right? Because if it has more energy levels as an atom, it's also going to have more energy levels as an ion. If barium becomes a +2 charge, it's going to end up with 54 electrons, which is xenon. Right? If calcium has a +2 charge, it's going to end up with 18 electrons, which is argon. Right? So xenon has more energy levels than argon, so barium's still going to be the bigger ion. So there's what happens when you compare in a column and why these things occur. So barium is a much better metal than calcium is. It's going to be much more reactive if you try to let it behave as a metal, where calcium is going to be more likely to form covalent bonds, although it still isn't going to do that very often, but it'll be much more likely to do that than barium will. All right, so let's look at a different example. Okay, let's look across a row now and see how it relates there. So let's compare magnesium, which we know is in row 3, to chlorine. All right. So they're both in energy level 3. Right, so we know that since the energy level is the same, that doesn't affect the size. Right, energy level part doesn't affect the size. So that means what's going to affect the size of these two is the effective nuclear force. So the effective nuclear force is +7 for chlorine and +2 for magnesium. All right, and the reason for that is both of them, since they're in row 3, you have to look at neon at the end of row 2 to figure out how many inner electrons there is. So that means for both of these, they have 10 inner electrons. So magnesium has 12 protons, 10 inner electrons. That's why you have a +2. Chlorine has 17 protons and 10 inner electrons. That's why it's +7. Right? So chlorine is smaller. Right? And we know as you go across the row, it gets smaller. There's the reason why. This is the explanation you want to give. All right, so what does that mean? It means that the ionization energy of chlorine is much higher, which means chlorine is less likely to lose electrons than magnesium would. It means that the electronegativity of chlorine is much higher, which means chlorine's the one that's more likely to gain electrons when it's sharing them with something else in a covalent bond. It means the electron affinity is higher. Which is more negative, right? Meaning that when chlorine gains an electron, it's going to be exothermic. Chlorine's going to get that stability by gaining the electron, because we know that the stability comes from the electrons being evenly distributed around the nucleus and not having places that have more positive or negative charge. Or should I say, around the nucleus, less negative charge versus other areas that has more negative charge. So chlorine is going to get that balance around the nucleus by gaining an electron, which means it's going to be very exothermic when it does that. While magnesium's not going to get that balance, it's actually going to become more unbalanced. So magnesium's electron affinity is more likely to be positive because you're breaking up its ability to have all the electrons nicely and neatly paired. So chlorine is expected to have a negative electron affinity. And so the ionic radius is a much more interesting discussion here, because now they're not going to mimic the even though they're in the same row, they're not going to mimic the same noble gas when they become ions. They're going to mimic different ones. And so we have to account for which one they're mimicking. So magnesium's going to lose 2 electrons, and when it does that, it's going to mimic neon. Chlorine's going to gain an electron, so when it does that, it's going to mimic argon. So because of that, argon we know has 1 more energy level than neon does. Magnesium is going to get significantly smaller as an ion than chlorine will. So since neon is fewer energy levels than argon is, magnesium is going to be a much smaller ion than chlorine is. And that's typically what happens with cations. Cations get significantly smaller, where anions get larger when they form compared to their original nuclei. So there's if you have them both in the same row. All right. So what if we change this and just had the ionic radius conversation, and we were looking at, instead of magnesium with chlorine, magnesium with fluorine. All right, it's hard to compare the other ones. You know, it's hard to compare ionization energies and electronegativities and all those things with things in different rows. You know, obviously fluorine is above magnesium. Energy levels plays a much bigger role in that. But when we start talking about ionic radius, we can compare these two very, very easily and have a logical answer as to which one is going to be bigger or smaller. Both will mimic argon as an ion. Right? Fluorine is going to gain an electron to mimic argon and have 10. Magnesium is going to lose 2 electrons to have the same electron configuration as argon, which is 10. So the question is, which one's going to have the bigger or smaller radius? The answer is magnesium has a smaller radius. And the reason it has a smaller radius is because magnesium has 12 protons and 10 electrons as an ion, right? Where fluorine as an ion has 9 protons and 10 electrons. So you can see the effective nuclear charge for magnesium is going to end up being much higher here because of the fact that it has more protons. So this is going to end up making the magnesium smaller as an ion than the fluoride ion will be. Okay, so that's the way you compare elements if they're in different rows with each other to figure out which one is going to have the bigger or smaller ionic radius. All right, so it's important to note what happens to them as ions, because this actually has a lot related to how strong the ionic compounds are based on the size of the ions. Smaller ions make stronger compounds, tend to be more insoluble or less soluble. That's why magnesium fluoride is used a lot in KSP problems. There was actually several AP questions using that for KSP problems. And so you want to be able to tie that in with atomic theory. That's a very, very likely relationship that they're going to look for to tie that atomic theory and periodic trends in with your size of ions and the strength of your ionic compounds, and therefore its likelihood to be soluble or not. All right, the other thing in Chapter 7 that is important is to understand successive ionization energies. This is where you're going to plot the first electron, see how much energy that took. Then you're going to plot the second electron, see how much energy that took. Then the third one, then the fourth one, then the fifth one. You keep going and keep going and keep going. And we want to try to then identify, well, which element was it based on how much energy we need to put into it to get the electrons out. So what you want to recognize is that the largest amount of energy that you would have to put in would be to pull an electron out of a completed energy level, right? Largest ionization energy is to remove electron from full energy level. And again, if you're removing an electron from a full energy level, then you are breaking up that even distribution of charge and that stability that the atom has. So, you know, removing it from a noble gas, removing an electron from a noble gas is going to be a lot of energy. So anytime you have a noble gas configuration, there's going to be a huge value for the ionization energy for removing that electron. Next largest would be removing an electron from a full sublevel. Right, removing an electron, the first electron for zinc, where you have that S filled or that D filled, that's going to break up, again, that stability, that balance of the electrons that you have around the nucleus. So anytime you break up a sublevel, start pulling electrons out of that, you're going to see an energy transition there too. And then also notice change breaking up half-filled sublevels. Right, so the half-filled sublevels also have some sort of even distribution of charge. It's not as good as a full sublevel, but there is some stability related to having like one electron in each of the p orbitals. And if you try to pull one of those out, you're going to see a change too. But you will always have the values increase. It's always going to be the easiest to remove the first electron and get progressively harder as you remove more and more electrons from it after that. So you always expect your ionization energies to go up. You're going to notice that there's going to be, like, if you remove an electron and then you remove another electron, whatever the difference was between those first two, it would be double that if you were removing it from a sublevel. It would probably be triple that if you were removing it from a full sublevel, and it'd probably be 5 or 6 times, maybe even higher than that, if you're removing it from a full energy level. So that's the way you can recognize. So they'll tell you what energy level the element is in, or what row in the periodic table the element is in. And what you do is you count to see where your largest is, your largest change, and that will let you know when you switched energy levels. So let me get some numbers. I'll write some numbers up here, and then we'll talk about what element it might be. Okay, so here's some successive ionization energies. So we're going to be told what row it's in. So this is going to be a row 3 element, right? They told us that in the problem. So it's going to be something in row 3. And so we start scanning our ionization energies. These would all be in kilojoules per mole. We start scanning our ionization energies, and we look for where we have huge increases. And I think the biggest increase is pretty obvious to be right here, right? We went from 4,356 to 16,000. That is a pretty huge increase. All right, so this is going to be where we reached our inner electrons, or our noble gas configuration. So this is actually removing that electron from the noble gas configuration, which means that this would be when my configuration matches neon, right? Because this, if it's a row 3, this is where I'm going to be removing the outermost electron from the second energy level, which would match neon's electron configuration. So that means that each one of these that I removed before that is going to be one more than neon. So if this is neon, right, then the one I removed before that would be the electron that would have the same configuration as sodium, 1s2, 2s2, 2p6, 3s1. And then the one before that is going to be the one that I removed from magnesium. I'm just going to do this, neon 3s2. And then the one before that is going to be neon 3s2, 3p1, right? Which would be aluminum. And then the one before that is going to be neon 3s2, 3p2, which is going to be silicon. So my element then that would have these ionization energies is going to be silicon, right? So we can see that when we get here, there is kind of an increase, right? This is kind of significant, but that's not as obvious. The one that's obvious is right here, and that's where we changed energy levels. So this one is removing the outermost electron from the previous energy level, and then you can count backwards, or count forward, if you will, on a periodic table to find out what element you're dealing with. Right? So then it's just a matter of understanding the properties of metals and nonmetals that are related to these things. So the more metallic your element is, the more likely it is to lose electrons, the more likely it is to be good at conducting electricity, conducting heat, the more ability to shape it you have. And these are some of the things that start coming up when we talk about states of matter, and we're talking about the difference between metals and nonmetals and metalloids and all of that stuff. So we'll come back to that stuff later on, but understanding the periodic trends and how it relates to all of this stuff and understanding how to use the periodic table to predict these things will make your understandings of lots of other topics much better. So that's the end of Chapter 7.